Problem 6, spicy reals. Let S be a subset of the positive real numbers with the property that for every real number x, the set of all y in S which are greater than x has a minimum element. Determine whether S is necessarily countable. To work through this problem, we're going to first try to give a bit of intuition for why it could be countable, and then using that intuition, try and come up with an explicit injection or bijection to the rationals, the integers, sigma star, any set which we know is countable. So without further ado, let's start with a bit of intuition. And for that, let's look at the number line because this is a subset of the positive real numbers, so it makes sense to start with the positive real numbers themselves. Here we have the number line from 0 onward. We know that there exists some minimum of y and s where y is greater than 0, and we can call this z. We know that such an element exists because of the property given in the problem. We can continue this process a little and say that there exists some minimum of the set of y and s that are greater than z itself. And really, we can keep continuing this process over and over. We can say, okay, well, the min of all elements which are greater than this min, and so on. And we can, in such a way, really enumerate all elements of S. And something to note is that these elements have gaps between them. In particular, we know there's some gap between 0 and z. We know there's some gap between z and this next element, the min of things greater than z. So one thing we could try first is to ask, can we find a distinct integer in each range if we're trying to prove that it is countable? And the ranges, as it turns out, aren't big enough. So for example, we can consider a set such as 0.9, 0.99, 0.999, and so on. And eventually we're going to reach 1 as our limit of this set. So in this case, there are no integers whatsoever in any of the intervals, but this set S is still countable. So if we can't find a distinct integer in each range, maybe we can still map in some way to the integers themselves. One way we could try doing that is trying to map some z, so the z that we calculated before, to 0. Then we can map the next element, this horrid term, to 1, and continue going on this way. Try and map each element to the next natural number based on its position. While this is also a good idea, it fails with the same set S. We know that S contains 1, but the issue is that 0.9 will get 0, 0.99 will get 1, 0.999 will get 2, and so on, and we're never going to actually reach 1. So in this case, this function does not actually map every element of the set S. However, this seems pretty close to what the right answer should be. We've mapped almost everything. Maybe we just need a little bit more power than just the natural numbers. And as mentioned before, there are a lot of countable sets that we have at our disposal other than the naturals. For example, one of these sets is the rational numbers. And that's what we're going to try and do next. We're going to try to map to the rationals by picking some element within this range, like between z and w, for example. We can find some rational number between z and w. Similarly, we can find another rational number between w and the next biggest thing. And then we can continue this process over and over and have a rational number in between each interval, which we're going to map z2, for example. And we can continue doing this for all elements of S. In particular, we can consider an element of S and consider the next biggest element of S and say, okay, well, can we find something there in between this element and the next element? Some rational number, and we can assign the smaller thing to this. So yes, this is in fact an injection because all of these rational numbers, no two of them can be the same. because of our ordering. We said R, for example, here was between Z and W, and then we said S was greater than W. So no two such numbers can be the same because of the intervals we put them in. And so we're done. We've shown an injection, therefore S is countable, and that's it. Now, we should note a disclaimer before going on. So we claim without proof that we can find such a rational number. Although this fact is true, it is not the main point of this proof. It is something that can be provable and is proved, but we just take it for granted here because that's not what we're going for when we're trying to prove this statement. And so with this disclaimer in mind, we have the full solution.